Hi there, everybody. This is the last section, and I'm sure you guys are super happy about that. And it's called L'Hopital's rule. A lot of you guys already know this, but I'm going to go over it because even though it's not strictly part of the course, if any of you are transferring to another college, you'll need it for Calc 2. If you're staying at LCCC, you'll get L'Hopital's rule again in Calc 2. And for the rest of you, if this is your last math class, then this is a nice application of calculus that lets us solve problems that we had trouble solving earlier, but we'll be able to do it now. So let's jump right in. So earlier sections, we saw things like these. So, you know, this one right here, this limit came up in the very first section we ever did. This came up when we did integrals, and obviously this is one section ago, and we solved all these limits. Here what we did is we factored and canceled. Here we simplified algebraically, and here we opened the function up and simplified. But we're going to look at easier ways to do some problems, and even how to solve some problems we couldn't solve before. So there were 7 types of indeterminate forms introduced earlier in the class. And we mostly dealt with these two here, right? We dealt with this kind in Chapter 1 and in Chapter 2. We dealt with this kind in Section 3.4, but there's actually all of these other ones. And we actually saw one that looks like this in Chapter 6 earlier, but we didn't call it an indeterminate form. So whenever a limit is in an indeterminate form, limit laws can't be used. And at the time, we were required to use algebraic or geometric solutions. We did some geometric solutions in Section 2.4 when we did our trig limits. And we've done algebraic solutions, obviously, Chapters 1 and 2. So now we're going to look at L'Hopital's rule. And so the motivating concept here is that let's say we have these two functions, natural log of x and 1 minus x. And so both of the limits, as x goes to 1, both of the limits go to 0. And so what happens is that when we stack the limits, if we looked at the quotient, what's the limit of the quotient? What would we do? We would make a table, right? Which means we would be zooming in on the point x equals 1. And this is an indeterminate form, right? If we plug in 1, we get 0 divided by 0. So if we zoom in, what we see is that the graph flattens out. So the more we zoom in, the flatter it gets, right? So this isn't actually a linear function, but this red function, right? The red function isn't, right? So what happens? Well, when we zoom in, it looks like we're taking a derivative. That's what it appears to be. So that tells us that we should be able to replace these two functions with their derivatives, because the derivatives, what is a derivative if not just flattening the function all the way out and actually turning it into a linear function? So it turns out that's how it works, and it's called L'Hopital's rule. So the idea is the functions have to be differentiable, and the limit of both functions has to be 0 for this version. There are 7 versions of L'Hopital's rule. I'm only going over a few of them, not going over all the versions. You don't have, you only have 4 of the 7 possibilities on your homework. So that's what it says here, right? The limit is x goes to a. A doesn't need to be a number, right? A can be infinity. This works for limits at infinity. It just says you take the derivative of the top and the bottom and you look at the quotient. And again, the justification is if we're zooming in on this point, like we would with a table, that zooming all the way in, if it's as flat as it can possibly get, that's just a derivative. So here's the proof for the special case of 0 divided by 0. And the special case we're looking at is the same one we just saw, except we're tacking on the special condition that the derivative is not allowed to be 0. There is a more general case that I'm not going to prove. The proof is in the book. So let's look at the limit as x goes to a of f prime over g prime. So what is that equivalent to? Well, that's the same as f prime of a over g prime of a. Remember, these are continuous and differentiable. Well, if they're differentiable, they're continuous. And f prime of a and g prime of a are both 0. So it's similar to that picture, right? If you go back, it's like this image. The function is 0 at a, right? And because they're continuous, you can plug in each individual limit, right? Now, it's still indeterminate, right? This is saying this is 0 over 0, but we're going to do some algebra and get some stuff to cancel. So here we're using the definition of a limit established back in section 2.1. I mean the definition of a derivative. Sorry, this is the definition of a derivative. And what's going to happen here is these are both have x minus a in the denominator, so I can take these two limits and pull it to the front. These are continuous, so I'm allowed to do that. And the limit exists, so I'm allowed to do that. Then I'm going to cancel these x minus a's. And now here's where the proof gets interesting, right? We just said that f of a and g of a are 0, so you plug in 0. Well, that's just f of x over g of x. So look at what we're saying here. If all of these things are true, f of a, g of a are both 0. G prime of a is not 0 because that would be this. That would be this. And differentiable, that this limit is the same as this limit. So we're actually working backwards from the derivative, just so you know. So the general form 0 divided by 0 is a little bit different, but this proof should make it believable that L'Hopital's rule works. I'm not doing the proof. It's actually pretty long. It's in the book. All right, so we're going to use L'Hopital's rule to find these limits. So here's two nice limits. We've already seen this one earlier, right? We know what this is, but let's solve it using L'Hopital's rule and see how it goes. And be sure to indicate at what step you're using L'Hopital's rule. So I just want to point this out that on a test, if you're not telling me where L'Hopital's rule is happening, you're going to lose probably half points. So if it's a 10-point question, you're going to lose 5 points for not indicating, I need to know what step it's happening. So I use a little H just in a little box. I've seen people use plus signs because the word hospital, it's like a mnemonic thing. All right, so let's jump in. Now, another thing we want to look at is to verify the limit is in an indeterminate form before trying to use the rule. So here's the limit we're trying to evaluate. So you want to look at the limit as x approaches 1 of x squared minus 1 and the limit as x approaches 1 of x minus 1. So you want to look at these two things separately, and you want to show that these two things separately are both 0. Later on, we're also going to do one that has different things, but for now, for this first example, we want them both to be 0, and they are. So that means this is in an indeterminate form, which means we can use L'Hopital's rule. So L'Hopital's rule says if you're in the indeterminate form 0 divided by 0, that you can just take the derivative of the numerator and denominator, and it's the same limit, that the limit doesn't change. You also must indicate where you're taking L'Hopital's rule, so that's where I'm doing it. And all I do is put a little H with a box, just, hey, here's where it's happening. It literally takes half a second to do, 5 points. Can't beat it. So derivative of x squared minus 1 is 2x. Derivative of x minus 1 is 1. Plug in the limit. Very, very easy. So is this easier than factoring and canceling? Probably not. But L'Hopital's rule will always work, except for a few tiny instances where it doesn't. Those are outlined at the end of the notes. All right, what if we have this limit here? So we had an algebra solution for problems like this early on. Let's see if we can do this with L'Hopital's rule. So we verified that it's indeterminate, right? So sine of 3t, we can plug it in, it's a continuous function, right? So sine of 3 times 0 is sine of 0, which is 0. Same thing, limit of 8t, that's 0, because 8 times 0 is 0. You don't have to show arithmetic. So this is indeterminate, so we use L'Hopital's rules. So we just take the derivative of the top and the bottom. And don't forget to indicate where you're doing it. So the derivative of sine of 3t is it's 3 times cosine 3t. And the derivative of 8t is just 8. Plug in 0, so we get 3 times 1, which is 3/8. So is this easier than the other method? They're about the same. What we're going to see as we progress through is that L'Hopital's rule is the only way to do some things, and it makes other things much easier. All right, now we're going to look at the infinity divided by infinity version. So again, differentiable and on an open interval. One thing I want to point out here is that most of the time, this a will be a plus or minus infinity, but it's not required. This works for vertical asymptotes as well. And I'm not doing the proof of this one. It gets real advanced real fast. So if f of x is plus or minus infinity, g of x is plus or minus infinity, look at the rule here. It's the same rule, that you just take the derivative of the top or the bottom. I'm sorry, top and the bottom. And this limit is the same as this limit. So let's see how this works. So we got 3 of them here. So what's interesting about this is for most of these infinity divided by infinity, there's really no other way to do these. So we have no other way of solving u over e to the u. We just don't have any way to solve that. So L'Hopital's rule is the only thing we can use. So again, verify that it's indeterminate. So the limit of u as u goes to infinity is infinity. The limit of e to the u as u goes to infinity is infinity. So it's indeterminate. We can use L'Hopital's rule. So take the derivative of the top and the bottom. Don't forget to mark where you're doing L'Hopital's rule. Derivative of u is 1. Derivative of e to the u is e to the u. Right, so that's basically 1 divided by infinity, which is 0. And I want to point out something here. This is not technically proper mathematical notation, but I will allow it if it helps you keep track of your steps and just keep working towards the goal, which is writing this as a number. Right? So I will allow this, even though there's lots of math teachers that just won't allow it. They would force you to go right from here to here, even though we don't have a rule that lets us go from here to here, right? We have to show that we're allowed to do that, right? So that's kind of the way that I show it. Like 1, so here infinity just means very large positive number. So the idea is that 1 over a very large positive number is 0. So that kind of shorthand is fine, even though it's not technically correct. All right, let's do another one. So here, natural log of x, that limit is infinity. Radical x, that limit is also infinity. So we have our indeterminate form. And so we just take the derivative of the top and the bottom. No big deal. I went ahead and just did all the simplifying and the exponents and stuff. You guys know how to do derivatives. So you end up with 1 over x over 1 over 2 radical x. Now you might be tempted to just plug in infinity and see what happens. And when you do that, you end up back in a previous indeterminate form of 0 divided by 0. So what we're going to do is simplify first. If we need to keep doing L'Hopital's rule, we can keep doing it. Hopefully we don't need to keep doing it. Let's hope this solves our problem. So there's my limit. So you're dividing fractions, so you flip and multiply. So now you have a radical x over x, simplify that. And when you plug in infinity, again, I would allow you to write 2 divided by infinity, but this is the more proper way to write it. So this is all the steps you'd have to show. If this is a test question or something, this is it. You don't have to show anything more than this. All right, let's keep going. So here we have e to the x over x squared. So check that both of these are infinity or both 0, and they are. Take the derivative. Don't forget to mark L'Hopital's rule. And we end up with e to the x over 2x. But this is still an indeterminate form. So we use L'Hopital's rule again. Which is pretty basic. So there you go. So those are by far the two most common instances of L'Hopital's rule that you'll see. Now there are more. I'm going to go through them. You don't have much of the other types on your homework, just a few. But you do have to know about them, especially those of you moving on to more math classes. L'Hopital's rule comes up absolutely all the time, and you don't have any warning. You might be doing a problem that involves limits 3 classes from now, and you might get to a point and go, I don't know how to do this. Oh yeah, I got to use L'Hopital's rule. So it does come up absolutely all the time from this point forward. All right, our next rule is the 0 times infinity version. So here, the limit of f of x as x goes to a is 0, and g of x is either plus or minus infinity. So our strategy is you have to take whatever your product is, and you have to take one of the functions and put it in the denominator to get 0 divided by 0. Okay, so whatever function is infinity, if you put it in the denominator as 1 over, it'll be 0 over 0. If you put the 0 function in the denominator, it'll be infinity over infinity. And the rule is the same for 0 over 0 or infinity over infinity. So it really doesn't matter which one you do. Just pick the one that makes L'Hopital's rule easier to evaluate. Like this one here. So I have u times e to the minus u. So which one of these do I want to put in the denominator? Do I want to write it as e to the minus u over e to the minus, or u to the minus 1? Probably not. It's probably easier just to write it like this. Again, you got to check infinity times 0. Make sure it's in your indeterminate form. But it's easier to write u e to the minus u as u divided by e to the u. And then we solved that problem in the previous example. So that's it. There's nothing more to it. If you have an infinity times 0, pick one of the functions and put it in the denominator as a 1 over. Right? So 1 over e to the minus u is e to the u, right? And that's it. And so you just get 0, right? We already solved this problem earlier. So no matter what form your indeterminate limit is in, you're trying to get it back to 0 divided by 0 or infinity divided by infinity. Now let's look in general. So there's actually 4 more types. And the general strategy is always convert from the existing form into infinity over infinity or 0 over 0. And then L'Hopital's rule, we're allowed to use it. If you have a infinity minus infinity or negative infinity plus negative infinity, involves finding common denominators, factoring, or multiplying by a conjugate. We're going to see one of those because these get pretty involved. The forms with that have exponents. So these other 3, I'm not giving you any of those on the homework. These tend to be much more advanced. You guys will see those in Calc 2. All right. And they don't come up that much, but the first 4 definitely come up a lot. And if you had to do L'Hopital's rule with exponents, you just need to take the natural log of both sides and bring the exponent to the front, evaluate, and then exponentiate to solve. All right, so here is a infinity minus infinity. So once you start getting into this type of form, a lot of wacky stuff can happen. Here's a good example. So you might be tempted to say, oh, well, this is infinity minus infinity, but it's actually not. If you're coming from the right, it's infinity minus infinity. If you're coming from the left, it's negative infinity minus negative infinity. How do we know that that limit exists? Because if I graphed the two functions here, right, I graphed x over x minus 1 and 1 over natural log x. There's nothing about this graph that tells me that this limit exists. And the individual limits don't exist, so why would the difference exist? Well, this actually came up. This comes up early in the class when we first talked about limit laws. This is why limit laws don't apply if the limit doesn't exist. So I'm not allowed to split this into two different limits, right? Because together, maybe this limit exists. But if I distribute that x minus 1, does not exist minus does not exist does not equal a number. So individually, these limits don't exist. But what about when I subtract? Does it look like this amount is converging on some value? So the graph shows us the difference between the two functions is small and positive. So look here. As we come in this way, it stays small and it stays positive. This function is always bigger than this function. What about on this side? It turns out this function is also always bigger than this function. So that tells us that if I'm subtracting, this is always a positive number. Does that positive number converge on a special value? It looks like it will. It looks like this is getting, I know it looks like it's getting smaller, it's actually not. The difference is staying pretty close, but as the functions sort of take off, that difference kind of stays. So just looking at the graphs tells us L'Hopital's rule works for the difference, even if the individual limits don't exist. So let's do L'Hopital's rule. So this is indeterminate form. From the right, it's infinity minus infinity. From the left, it's negative infinity minus negative infinity. And it turns out when we do it together and do that derivative, that we're going to get an answer. So how do I evaluate this? So I'm trying to get it 0 over 0 or infinity over infinity, which means I need to combine these fractions together. The only way to combine fractions is with a common denominator. So that's the next step. So the common denominator is x minus 1 times ln of x. Simplify. Now that it's as simplified as it can get, right, you still want to check that it's indeterminate, right? So plug in x equals 1. 1 times 0 minus 1 plus 1, so this is 0. Plug in 1 here. 1 minus 1 times 0 is 0. So now it's 0 divided by 0. So this is indeterminate form, so we can use L'Hopital's rule. So just because it showed up as a subtraction problem doesn't mean we evaluate it as a subtraction problem. As soon as we get the common denominator, it becomes a division problem. So there's L'Hopital's rule. Take the derivative of the top and the bottom. So did product rule here. Derivative of negative x is negative 1. Derivative of 1 is 0. Derivative of x minus 1 times ln of x. I did product rule and got this. So I'm not showing the details on these derivatives now. On a test, you would have to do it. But I'm trying to keep the videos under 35 minutes. Simplifying. So we did L'Hopital's rule once. Now what happens when we plug in x equals 1? Natural log of 1 is 0. 1 minus 1 over 1 is 0. Natural log of 1 is 0. So these two together is 0. That's it. Still 0 over 0. So we just have to do L'Hopital's rule again. Take the derivative again. This becomes 1 over x. This goes away. This becomes positive 1 over x squared. This becomes 1 over x. It is no longer indeterminate. I mean, it is if you just like plug in 0, but we're plugging in 1, right? So don't think that just because it's 1 over x that it's indeterminate. We're trying to plug this number in. Well, this is not indeterminate if we plug in 1, right? The answer is actually 1/2. So that might surprise you that something like this, that difference becomes a half as you get closer to 1. So very powerful tool, this L'Hopital's rule. All right, so that's it for the examples. Couple things. What can go wrong with L'Hopital's rule? Turns out a lot of things can go wrong, but they're rare. So L'Hopital's rule only works if the limit is in an indeterminate form, infinity over infinity or 0 over 0. If you need to manipulate the equation to get it to look like this, totally fine. So if you have infinity times 0, you have to put one of them in the denominator as 1 over that thing. If the limit is not indeterminate or not in the correct form, L'Hopital's rule will give the wrong answer, right? So here's a good example of L'Hopital's rule giving the wrong answer. So here we have a limit. This is a problem we would have done in chapter 1. Evaluate this limit. Well, it's not 0 over 0 or infinity over infinity, so you just plug in 3, right? So 2 times 3 is 6, minus 1 is 5. 3 times 3 is 9, plus 2 is 11. So you get 5 11ths. But what happens if you just try L'Hopital's rule? Does it work? Take the derivative. Well, that's 2/3. 5 11ths is not the same as 2/3. So what went wrong is that L'Hopital's rule only works if you need it. It can't be used just in every conceivable situation. And another thing that goes wrong is sometimes L'Hopital's rule gets stuck in an infinite loop. Let me show you what I mean here. So look at this function. If you plug in infinity, you get infinity over infinity. So this is infinity minus 0, infinity plus 0. So infinity over infinity, you might think, well, that's 1. But will L'Hopital's rule give us 1? So you take the derivative, and all it does is it flips the signs. Well, this is still indeterminate. Let's take L'Hopital's rule again. Now we're back where we started. Sometimes L'Hopital's rule gets stuck. Luckily, whenever this happens, we have other ways to solve these problems. So how do we avoid mistakes? Well, you always verify the limit is infinity over infinity or 0 over 0. If not, it won't work. Or eventually, it has to be in that form for you to do L'Hopital's rule. It doesn't have to start in that form. It just has to get there to use L'Hopital's rule. If the limit is not indeterminate, use methods introduced in earlier chapters. If the limit is indeterminate but not of the proper type, use the methods we just talked about, right? Common denominator, writing one of the functions in the denominator as 1 over the function, and then taking the derivatives. And if L'Hopital's rule causes the limit to get stuck in an infinite loop, try using a different method. So what about the methods from earlier in chapter 6? Earlier in chapter 6, we would have tried to divide through by the highest power in the denominator, right? That's what we did in chapter 2 and chapter 1. Well, the highest power here is e to the x, so dividing by e to the x is the same as multiplying by e to the minus x, so multiply through, and that's a really easy limit, right? That's what we thought it was going to be. We thought it was going to be 1. This is how you would prove it. So you just have to be a little bit careful on an exam. If I say use any method we've covered, then L'Hopital's rule is fine, but that doesn't mean that it's the best way to solve it. You could be stuck in an infinite loop. So don't think that L'Hopital's rule is a one-size-fits-all. It's not. It's a powerful tool, but only use it if you need it, or if you think it'll make things easier. But if you start noticing infinite loops, or you start noticing like it doesn't simplify or something, try using an algebra method, and it'll work. All right, that's it. There is one more historical note. I'll let you guys read that. And here there's a nice video. Of course, the ebook always has the good videos. Lots of practice exercises. And of course, lots of online resources. So if you have questions, this will be on the final exam. But just like an ordinary exam question, like one question. So if you have questions, shoot me an email or post on the discussion forum. And that's it for lectures for the entire class. Hope you guys learned something and study hard for the final. Bye-bye now.